All right, hello everyone. So last time we had a lesson about trigonometric graphs, and we really just focused on sine and cosine. I think in the previous lesson I told you that those are the two most important trig functions, but there are also other trig functions too, and they do have some importance. So what this lesson is going to be about is more trigonometric graphs, where we look at the graphs of tangent, secant, cosecant, and cotangent. Uh, so I think this lesson might be a little bit shorter. We'll see how it goes. Let's get started. All right, more trigonometric graphs. I should mention some of the things that you should know from last time is you should know the graphs of sine and cosine. You should know how they relate to the unit circle. And you should know how to graph transformations of sine and cosine. For example, we did some examples like y equals 2 plus sine x, or y equals negative cosine x. Basically, starting from sine or cosine, but with some graph transformations. All right, let's talk about the unit circle again so that we can talk about tangent and the other ones. So first of all, suppose t, a t value is how far we go around the unit circle. Suppose t has terminal point x comma y. Here's a question for us to think about. What is the terminal point of t plus pi? Let's think about this together. Is the terminal point going to be related to x comma y in some way? Let's draw a picture. By the way, if we did t plus 2 pi, if we did t plus 2 pi, I know what the terminal point would be, right? Side note, the terminal point for t plus 2 pi would be x comma y, the same terminal point that we started with from t. So, if you go t around the unit circle and then you go an extra 2 pi, it takes you to the same place, right? So that's just a little side note. We've seen that actually in action. We've seen that happen because we had one example where we did pi over 2, took us to this terminal point, and then we had an example where we did 2.5 pi, which is exactly pi over 2 plus 2 pi, which means, we went around the unit circle an extra time and wound up at that same terminal point. So if you add 2 pi to t, you get the same terminal point. What if you only add 1 pi? Let's see what happens. Let's draw a little t value here just as an example. Let's say I go that far. We've gone t around here. I'll mark it where, like, here's the terminal point, x comma y. I'm also going to indicate kind of a t in here. Maybe I can zoom in on this. All right, see what I've done so far? I went t around the unit circle. I got to a terminal point x comma y. All right, what if we add another pi? Like, instead of just t, it's going to be t plus pi. So we went t, and now we go pi around the unit circle. Well, pi is supposed to take us halfway around the unit circle. So adding plus pi would do this. This is the plus pi. What terminal point does it take us to? I'm over here. We've gone a total distance of t plus pi, and we arrive at some kind of terminal point. It looks to me like it's directly across. It's on the other side of the world, right? It's exactly directly across from x comma y. And using what we know about reference numbers, the idea is that this is going to be some form of x comma y. We just have to figure out if there are pluses or minuses in front. And because of what quadrant it's in, I can see that this would be minus x minus y. So that's the answer to this question above, is minus x minus y. Let's zoom out so we can see everything again. All right, well, we'll see how that helps us. Let's talk about tangent. Remember, we said that tangent of t equals y over x. So, what is tangent of t plus pi? It would be this y coordinate over this x coordinate. So negative y over negative x. But negative over negative just becomes positive. So this is y over x. So if I do tangent of t plus pi, I just get the same thing as if I had done tangent of t. We'll say, therefore, tangent of t plus pi equals tangent of just t. What does this mean? What does this mean for us? Like in words, what do you think that means? This means tangent repeats after pi units. In other words, what do you think is another way we could say this? Tangent has period pi. So this is different from sine and cosine. We said that sine and cosine had a period of 2 pi, and that made sense when we talked about those. Now we're focused more on tangent, and we're seeing that tangent has a period of only pi. So whatever curve, whatever shape we get when we draw the graph of tangent, I would expect it to repeat itself every pi units. Every pi units we go over to the right, or pi units we go over to the left. Okay, let's talk about the other trig functions as well. And what I've decided to do is we're going to talk about tangent and cotangent together. And I'll tell you that tangent and cotangent both have period pi. We basically just derived that idea for tangent. We basically just explained why tangent has a period of pi, and you could do something similar to figure it out for cotangent. So if we were to write tangent or cotangent as functions of x, like last time when we were graphing, we started talking about y equals sine x, y equals cosine x. So I'm going to switch to x's here. Probably use x's for most of the rest of the video. Tangent of x plus pi equals tangent of x. I guess we would say that this is true for any x in the domain. And cotangent of x plus pi is equal to cotangent of x for any x in the domain. Now, since we're talking about domain right now, I'm going to go ahead and tell you that cosecant and secant, because cosecant and secant are the reciprocals of sine and cosine, they wind up having a period of 2 pi. We could go into more detail about deriving that fact, but for the sake of time, I decided that I'm just going to say this here. I think it seems believable because cosecant is based on sine, secant is based on cosine. So of the 6 trig functions, sine, cosine, tangent, cotangent, right? Out of these 6, 2 of them have period pi. The other 4 have period 2 pi, meaning that's how much of the curve you have to draw before it repeats. Let's get a new sheet of paper and let's start drawing the graphs. And we're going to start by drawing the graphs of tangent and cotangent. And I think we'll spend some time graphing tangent. We'll focus on that one the most. So graphs of tan, and remember cotangent can be abbreviated COT. How about we do a little table of values? Didn't that help us last time? We kind of found a few values. So I'm going to say, let's set up x and tangent x. Let's do some common values of x. So 0, pi over 6, pi over 4, pi over 3. I'm going to leave some space here for something that I want to show you. Let me straighten out my paper here. I'm going to leave some space underneath pi over 3. Skip down a bit and put pi over 2 here. Okay? And we'll figure out tangent of these values. We could do a little scratch work over here to help figure these out. We had a table of common terminal points, and that means that we should know sine and cosine of these. Like if I asked you what's sine of pi over 6, you should be able to figure that out. You could draw a quick little scratch work unit circle if it helps you remember which point it is. If I asked you what's cosine of pi over 3, what's cosine of pi over 4, sine or cosine of pi over 2, you should be able to know those. But tangent takes like an extra step. So that's why I'm going to say let's do some scratch work. Let's figure out tangent of 0. The way that I like to think of these is I like to think of them as sine over cosine, because that's what tangent is. And in this case, it's 0 over 1, which is 0. So it looks like on the graph that we eventually draw for tangent, we're going to pass through the point 0, 0. It's right here. 0. You can imagine a comma. 0, 0 is a point on the graph. For this one, what is tangent of pi over 6? So it's sine of pi over 6 divided by cosine of pi over 6. And you should know sine of pi over 6 is 1/2. Cosine of pi over 6 is the square root of 3 over 2. This winds up equaling 1 over the square root of 3. I'm not leaving myself a lot of room here, am I? I think we saw this. Well, you know what? Let's just do it. I'm getting whiteouts. I put an equal sign there, and I want to get rid of the equal sign. That is what we got so far. 1 over the square root of 3. I want to rearrange it, rationalize the denominator, so to speak. We want to get the square root out of the denominator. So I'm going to multiply it by square root of 3 over square root of 3. What does that do for me? It turns the numerator into the square root of 3, turns the denominator into 3. And I'm going to tell you that this is approximately equal to, I found as a decimal, this is approximately 0.58. So for our graph, I'll try to go about that high. Let's work on this one. Tangent pi over 4. I'm sure we've done some of these, but this is going to be, let's skip a little bit of the writing. It's sine of pi over 4 over cosine of pi over 4. I know both of those are the square root of 2 over 2. So I have the square root of 2 over 2 divided by the square root of 2 over 2. That's a number divided by itself, so I get 1. What's tangent of pi over 3? Maybe I'll skip the scratch work for that one. I mean, you can do these, right? You could do this tangent of pi over 3, similar kind of way that we're doing these. Try to simplify it. You'll get the square root of 3 as your answer. Now, the square root of 3, here's what I'll do. I'll write it as a decimal, and I'll say that it's the square root of 3. Why am I writing it as a decimal? I said we don't use decimals very much in this course. It's because when we graph these points, I'm going to do pi over 3 comma 1.7, and that's going to be easier to do than figure out, like, where's the square root of 3. You'd probably have to think of it as a decimal anyway. In fact, I'm going to tell you some of these things as a decimal. So this right here, pi over 3 as a decimal, it's a little bit bigger than 1, right? Pi is a little bit bigger than 3. So this should be a little bit bigger than 1. It's approximately 1.05. And I'm going to tell you that pi over 2, you could probably figure out in your head like roughly what that is. It's approximately 1.5708. Let's keep that in mind for what we're about to do. All right. Right here. What is tangent of pi over 2? It is sine of pi over 2 divided by cosine of pi over 2, which is, think about where it is on the unit circle. Where's pi over 2 on the unit circle? Terminal point, get your y, get your x. 1 over 0. 1 over 0. So 1 over 0, we should say, is undefined. So are we finding points that we're going to be able to put together and make a nice graph? So far, I know we have the point 0, comma 0, pi over 6, comma this. We've got 4 points, and then at pi over 2, something is happening that's making this function undefined. That's different from when we worked on sine and cosine last time. Tangent is sometimes undefined. But we talked about the domain of trig functions in a previous lesson, so we knew that there were some places, there were some x values that are not in the domain. Pi over 2 is one of them. It's not in the domain because we're dividing by 0. I left some space here because I want to fill in some extra points here that I found with a calculator, because I'm basically wondering what is happening between this point and this point. We have pi over 3, comma, square root of 3. That's a perfectly valid point that will be on our graph. Something happens when we move to the right a little bit. The function is now undefined. So what's happening in between? And I decided to look at some points that are very close to pi over 2. So I decided to look at 1.5, and I found tangent of 1.5 is approximately 14.10. That's not something that I would ask you to find by hand, but there it is. And then I said, all right, what if I get even closer? I looked at 1.55. We can't go to 1.6 because then we've already gone past pi over 2. I'm trying to get close to this. I found with a calculator that this is about 48.08. And then I did one more. I said, okay, let's get really close and go to 1.57. That's really close to where it's undefined. And with a calculator, I found that this is approximately 1,255.77. Can you think in your head, can you like picture this in your head? What's happening on the graph in this area? You imagine these points? The y-coordinate is getting very, very large, and then all of a sudden it's undefined. This is going to be a vertical asymptote. That is what we're seeing here. Looks like a vertical asymptote. The closer we get to pi over 2, like 1.5, 1.55, 1.57, the larger the function gets until it's over 1,000, and then it's undefined. So when we graph this now, let's try to put an asymptote there. And then we do have 4 points that we can plot. So we'll have, well, actually, we could plot these as well, the 1.5, comma 14, you know, all that. So we have some points we can plot, and we say there's an asymptote here. So I'm going to start graphing tangent. I'm going to leave some room to the right because I would also like to draw a graph of cotangent after this. And for cotangent, we're not going to go through all the work of making a table and all that. Here's what we'll do. We'll just set up both. So this is going to be the graph of y equals tan x. And over here, we'll do y equals cotangent x. All right. Let's label x-axis, y-axis, x-axis, y-axis. What do you think we should put on the x-axis for some points of interest? I would say we don't really need to go as far out as 2 pi. When we did sine and cosine, we went out to 2 pi, but this is, you know, this has a smaller period. Let's put pi here. Let's put pi here, and that would mean negative pi is here. Let's fill in a couple more. So that means pi over 2 is here. Negative pi over 2 is here. And I'll go ahead and put one more. This is 3 pi over 2. And one more in this direction, negative 3 pi over 2. On the vertical axis, what kinds of points what kind of scale are we looking for here? Remember how sine and cosine had a max value of 1? That's not happening here. We don't have a max value at all. It keeps growing and growing. We actually said the range of tangent was, I think we said, well, maybe you're seeing it now. If we haven't said it before, the range of tangent seems to be all real numbers. It seems like we're able to go up and up and up forever. All right, I said it looks like there's a vertical asymptote at pi over 2, so I'm going to draw a dashed line. And as far as vertical scale goes, I don't know, let's just put a 1 here. And a negative 1 here. Let's say that's something, just to give us scale. Okay. If there is a vertical asymptote at pi over 2, there has to then also be a vertical asymptote pi later. Because whatever this function does, it has a period of pi, so it repeats itself pi later. Also, pi earlier. Pi to the left. And another pi to the left. Vertical asymptotes. Like that. We only really found one of these asymptotes on our table, but I'm saying that the other ones must exist because it's a periodic function. It repeats itself. Tangent of t plus pi equals tangent of t. So asymptote here, add pi, you get the asymptote again. Let's plot some points. We said that this graph goes through 0, 0. We said pi, how about one of them was pi over 4, 1. I could plot that. Here's pi over 4. Here's 1. Can we draw pi over 6, 0.58? Where's that? About here. That's my pi over 6, 0.58. What's another point we knew? We knew pi over 3 comma 1.73. Here's, say this is pi over 3, 1.73. I'm gonna zoom in on this now. See what we've got so far. The other points that I said we had, the 1.5 comma 14, 1.55 comma 48, they're going to be way up here. They're going to be way off the top of my picture, so maybe it's hard to draw those exactly. 1.57 comma 1255, that's way off the top of my page. But we know how asymptotes work. We know that this curve is going to approach the asymptote but never quite touch it. That's what it means to be an asymptote. And that is us illustrating that it keeps growing and growing. It grows to a height of 14, 48, 1200, and probably keeps going forever. Now, what's going on to the left here? Maybe I can show you something from a previous lesson. Let's find this in our notes. Well, I found my notes, but my notes are a little messy, so I'm just going to write it again down here. All right. In an earlier lesson, you don't need to see my messy notes, I'll just write it again. We said that tangent of negative x equals negative tangent of x. Okay, for all x in the domain. This was towards the end of the lesson. That was just the lesson called trigonometric functions, where we were introducing all the trig functions. And towards the end of that lesson, we talked about a few trig identities, and they were basically facts about how trig functions are related to each other. And this is one of the things we said. Tangent of negative x equals negative tangent x. In my notes, I see that we actually may have said it with the letter t instead of the letter x. But that's okay. That's just a label. Whether it's labeled t or x, same idea. Now, what consequence does this have on the graph? Like, why am I bringing this up now? I brought this up because it means we can figure out what's going on in this part of the graph based on this fact and based on the stuff that we already drew. It means that, take this point, for example. This point right here was at pi over 4, comma 1. It means there's going to be a point at negative pi over 4, comma negative 1. This point that I just drew. That has to be there because of this fact. The other points that we drew also have corresponding negative points down here. The pi over 3, comma 1.7 is going to have a corresponding negative pi over 3, negative 1.7. So this is kind of like a little shortcut. We didn't have to set up these values on a table. We got them from here. And we also know that if there's an asymptote here, the curve needs to approach the asymptote, but not quite touch it. So it's going to look something like this. Tangent definitely looks different from sine or cosine, doesn't it? All right, what's left for us to do? What's going on in these other areas? Is this the entire graph, or is there other stuff going on? Well, remember, this is a periodic function. And similar to what I said for sine and cosine, we have this idea that once you draw one period, we drew one period of it, didn't we? Can I indicate this here without making a mess? From here to here, this length is pi. So isn't that 1 period? So we went from negative pi over 2 to positive pi over 2. Do you see that? So we drew 1 period, and periodic functions are supposed to repeat themselves after that. So what happens is you can take what we drew and copy and paste it to the right. You can also take what we drew and copy and paste it to the left. And if you were to zoom out, you would also have another copy of it further to the left, and another copy to the left, and another copy to the left. And if you go to the right, you'd have another copy, another copy, another copy. It keeps repeating forever. Pretty interesting looking graph. Now, off to the side, I made some room for us to draw the graph of cotangent. And I think that we could go through the same process we did above. We could set up a table, find some values. We could figure out where asymptotes are. But I think for the sake of time, I'm going to just show you the graph of cotangent, because conceptually, it's very similar to what we just did. In fact, I'm going to set it up to have the same kind of scale, vertically and horizontally, on my picture. So pi over 2, pi, 3 pi over 2, negative pi over 2, negative pi, negative 3 pi over 2. All right, same kind of scale. The asymptotes are going to be in a different spot, though. Remember how tangent is y over x, but cotangent is x over y? So tangent is undefined anywhere on the unit circle where x is 0. And that, in the graph, wound up giving us asymptotes. Cotangent is undefined anytime y is 0 on the unit circle. Y is 0 on the unit circle, for example, at x equals 0. And we get a vertical asymptote here. What I'm saying is cotangent of 0 is undefined. Cotangent of 0 is undefined because we would be dividing by 0. And similar to tangent, it winds up showing up on the graph in the form of a vertical asymptote. And then because we have a vertical asymptote there, and because the period is 1, we must also have another vertical asymptote if we add pi. And if we subtract pi. I told you these graphs are going to look similar, so yeah, they've got asymptotes. So do you think it's going to kind of look like tangent, except it's going to be in here? Well, sort of. The main difference between tangent and cotangent is that it's like the x's and y's have been flipped. They are the reciprocal of each other, right? Tangent is y over x, cotangent is x over y. So they do have a similar looking curve, but flipped. So it's going to look like this. There we go. That is 1 period of cotangent. And if it looks like that for 1 period, we should be able to copy and paste it to the left to draw more pieces of cotangent, and copy and paste it to the left again. Maybe eventually you say, all right, I'm running out of space. Let's just cut it off here. And you could do the same thing on this side. So right here, we drew pretty nice graphs. I'm going to kind of section these off. Make sure that we don't have like one graph running into each other. We did good. Graph tangent, graph cotangent. Pretty different from sine and cosine. But ultimately still based on the unit circle. So what I'd like to do next is I'd like to move on and talk about graphs of cosecant and secant. So I'll be moving this away in just a moment. If anyone is still copying this, I would suggest you just pause and get what you need. All right, let's move this. Let's move all that because we need a fresh amount of space to talk about these other ones. So the graphs of cosecant and secant, they are the reciprocals of sine and cosine. And we, by the way, remember we said that they have a period of 2 pi. Okay. And remember that cosecant x is 1 over sine x, and secant x is 1 over cosine x. So, we have to remember that they are reciprocals, but we have to remember which one goes with which. We can use this reciprocal relationship to help figure out the graphs. We'll start with a graph of y equals sine x, which I'm going to draw in black, and use it to figure out what the graph of cosecant x looks like. And I'm going to do that in blue. All right. I'm kind of explaining the strategy, but let's go ahead and get started, and it'll start to become clear what I mean. So I'm going to start by drawing a picture of sine x because we know what sine x looks like. And I think I'm only going to draw one period. So sine x, which we drew in the previous lesson, has a maximum height of 1, a minimum height of -1. And by the time we get to 2 pi, we've shown a full period. Here's pi in the middle, x-axis, y-axis. I'm going to draw sine. And then I want to talk about, if we have the graph of a function, can we use it to figure out the graph of its reciprocal function? By the way, reciprocal is not the same thing as inverse, right? I'm not talking about, they're not like, cosecant is not the inverse of sine. It's the reciprocal. There's a difference. All right, based on this, can I figure out points in blue? Got my pen ready. Can I figure out points of cosecant? Let's do some work off to the side. All right, example. How about, I know that we could do these in any order, I guess. How about sine of pi over 6 is 1/2? That means that cosecant pi over 6 is 2. We flip it. Flip 1 over 2, you get 2 over 1. So I'm going to plot a point. It's going to be at pi over 6, comma 2. Oh, that means we need to let this graph go up to 2, don't we? Let's do that. Pi over 6, I'll say, is maybe here. There we go. That's our first point on the graph of cosecant. This is going to be a graph of y equals cosecant x in blue, with sine x on the picture as a guide to help us. All right, that was 1 point. Let's do another. How about sine of pi over 4? Sine of pi over 4 is the square root of 2 over 2. So cosecant of pi over 4 must be 2 over the root of 2. 2 over the root of 2. You can do our usual thing to try to rearrange this. Multiply it by the square root of 2 over 2. You will find that this actually equals the square root of 2, which is approximately 1.4. So we get a point at pi over 4, comma, 1.4, maybe about here. Let's continue this. What's sine of pi over 3? Square root of 3 over 2. What does that mean for cosecant? It means that cosecant of pi over 3 equals 2 over the square root of 3. If you multiply this by root 3 over root 3, you get 2 root 3 over 3, which I actually did not figure that one out as a decimal. Offhand, I don't know. It seems to me like that must be a little bit bigger than 1, because I know that square root of 3 is around 1.7, and we're doing 2/3 of it. It's a little bit bigger than 1, so I guess that would go about here. What's sine of pi over 2? Sine of pi over 2 is 1. So cosecant is the reciprocal of that. Cosecant of pi over 2 is the reciprocal of 1, which is 1. So we have a point at 1, pi over 2, comma 1. I almost said 1, comma 1. Pi over 2, comma 1. We've plotted 4 points on the graph of cosecant. How about this? Let's skip ahead a little bit. Let's skip ahead to sine of pi. What is sine of pi? Think about the unit circle, maybe. Think about what this would be. This is 0. So cosecant of pi is the reciprocal, 1 over 0, question mark. It is undefined. 1 over 0 is undefined. And similar to when we did tangent and cotangent just a few minutes ago, this is going to represent itself in the picture as a vertical asymptote, and it's going to happen at pi. So at pi, I have a vertical asymptote. In fact, I think we could say that anywhere that the graph of sine crosses the x-axis, those are the places where sine equals 0. Cosecant would be 1 over 0, which is going to be undefined. It's going to give us a vertical asymptote here as well. And here. Okay? Maybe this is enough points to sort of fill in some things. We know that curves have to approach asymptotes but not quite touch them, not cross them, not overlap with the asymptote. You know what? If we have these 4 points, you can kind of see what's happening as you go from the original function to the reciprocal, is the small values, like 1/2, become larger values, like 2. We have a point over here that looks like it's at a height of 1/2, and the reciprocal of it would be up here at 2. We have a point over here, it gets moved up, right? So you get this nice symmetrical shape. And what I'm going to do is connect these with a nice smooth curve and make sure that I do so in a way that approaches these asymptotes. So this is part of the graph of cosecant x. Does it look like a parabola? Maybe in a way, but I want to say not really, because a parabola would never have vertical asymptotes. Maybe like if you took a parabola and squished it in with asymptotes, but that's really changing it pretty drastically. This is really just its own thing. Now, what's happening in these other regions? Like what's happening here? Um, Remember, the period of cosecant is 2 pi. We've only drawn from 0 to pi. So actually, one period should be like this. This is the length 2 pi, one period. So I can't just I can't copy and paste what we already drew. Although maybe I could, but it has to be kind of over here, you know? Do this. That's fine. But what's going on? What's going on in this area? Nothing, or is there something? So let's use the same kind of reasoning and look at points on sine. So how about this point right here? On the graph of sine, this is the point 3 pi over 2, comma, negative 1. What is the reciprocal of negative 1? It is negative 1. Reciprocal of negative 1 is negative 1. So we get a point on the graph here. What if I looked at the graph of sine about here and said, this spot on the graph looks like it's at a height of about negative 1/2. The reciprocal of negative 1/2 is going to be negative 2. So I'm going to get a point here. I could make a similar argument for why there needs to be a point on the graph here at a height of negative 2. And altogether, we're going to get a curve that goes like this. So, oh, we could copy it over here as well, I guess. Go to the left, like that. Cool, so what we drew in blue is the graph of cosecant. What we drew in black was just kind of a guide. It was a graph of sine to help guide us. Okay. I think that usually when I teach this in person, I do it this way. And then I go up to the board with, with an eraser and I erase all the black. And then we're left with just the graph of cosecant. So maybe you could imagine doing that. I've got whiteout tape, but I think it would make a mess of this picture if I did that. So I hope that you can see that the black curve is the graph of sine x, which we used as a guide. The actual graph of cosecant is just what we have in blue. Pretty different looking function, right? It's got a lot of vertical asymptotes. It has an interesting range, doesn't it? Because it never actually crosses the x-axis. The blue curve never touches the x-axis. So I guess if you do cosecant of something, you're never going to get 0 as a result. You could get as low as a height of positive 1 here. You could get, actually, you could get as low as you want because you could go down, 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 right? So this goes towards negative infinity. There's just this kind of area in here that the blue curve never touches. Interesting that the cosecant and sine, they kind of touch each other here and here. So, what we've done so far today was we spent a bunch of time on the graph of tangent, and then I drew the graph of cotangent just to show you. Now, we spent a bunch of time on cosecant, so next I'd like to draw the graph of secant to show you without going through all this work, because conceptually it's the same kind of thing. If you can understand what we just did, then I'm confident that you could also do this for secant. So I'm going to draw it based on the graph of cosine. So I'll say graph of y equals secant x in blue, but I'm going to draw a graph of cosine to base this off of. So let's say here's a height of 1, -1, and let's go out to about 2 pi. Here's pi, -pi, -2 pi. Graph of cosine, remember, cosine passes through a height of 1, and 2 pi later, it's back up there. Sometimes I do this. I draw like some dots as kind of a guide, and then I fill it in with the curved shape that I know that it has. So cosine is what I'm drawing as a guide here. I probably should have drawn this in pencil so that we could erase it when we're all done, but that's fine. Okay, so this is y equals cosine x. Here's the idea. Anywhere that cosine x crosses the x-axis, anywhere that cosine equals 0, secant is going to be the reciprocal of 0, which is undefined. So at all of these places, we're going to get vertical asymptotes. Those are the places that are not in the domain of secant, and they happen to be vertical asymptotes. So draw a bunch of those. What do you think is going to happen with the rest of the picture after we get these asymptotes drawn? You could think about that. Period is 2 pi. Okay, we drew a lot of these. Drew a lot of those, didn't we? It's similar to the graph that we drew above of cosecant. Now we're doing secant, and it is also going to have a similar shape where it approaches these asymptotes, and it kind of touches the graph of cosine at these sort of individual points. So what I'm drawing in blue is the graph of secant. Interesting graph. Now imagine we erase the black curve because it was just there as a guide to help us. So I'll give you a minute in case you're copying that down. All right, so we made it. That's it. So this lesson was called More Trigonometric Graphs, and this lesson was really just about us becoming familiar with what do the graphs look like for the other 4 trig functions: tangent, cotangent, cosecant, secant. You should be able to recognize them. You should be able to draw them, right? Now that we've done it, you should be able to draw them. And I think it doesn't necessarily have to take you as long as we did today. It was about showing them to you for the first time and deriving why they look the way they look. But now that you know that this is what they look like, you can probably draw them quicker. Figure out where the asymptotes go, and you know the overall shape of the curve, and you fill in the curve. So what I'm going to say is, for these trig functions that we talked about today, for this section and this lesson, I'm not going to ask you about graph transformations. Okay, so what I mean is when we did sine and cosine, we did some transformation versions of them. We're not going to do that right now for these trig functions. We might do it in a later lesson, but you don't have to worry about it for now. You know, tangent x with a bunch of graph transformations applied to it or something like that. Okay, so what's coming up next? Next, we are going, now that we understand what the graphs of these functions look like, we're going to ask ourselves, are these functions one-to-one, and do they have inverse functions? That's one of the things we like to do when we introduce a new type of function, is talk about, is there an inverse version of it? If you see me kind of squinting or something or making a face, it's because they sort of have inverse functions. Sort of. We have to figure out how it all works. So that's going to be the next lesson. Okay, so I hope everybody is doing well. I hope you're having a good day or a good evening or whatever. And I'll see you next time. Bye.